Alright, so as we saw before, when we first start PVE we see the nozzle database dialog box, but what we also know is that everything will be in US units. So first of all, let's change our default units file. So first of all, click OK on this dialog box. Doesn't matter which option you've chosen, we're not going to use that here anyway. And then in PVE, go to this button here, the configuration parameters. Now within the configuration window, we can go to the default value settings page, and in here we can change various things, including the units file, which is here on the right hand side of the screen. So the default is the english.fil units file. I'm going to change this to one of the metric ones, such as newtons.fil. You can also create your own units file, but for this example I'm just going to stick with one of the out-of-the-box units files. As soon as you change that, you then see a message, these will be the default units next time you start PVE. So that's OK, and now we need to restart PVE. So I'm going to close and reopen the software. Alright, now I've restarted the software. As we can see in the background, the units is now the newtons metric units file which I've chosen. So let's start and build a vessel. I'm going to use the ANSI metric nominal pipe size for the nozzle database here. So the units for nozzles will be millimeters. So we have 100, 150 nominal size nozzles rather than 4 or 6 inch. So OK. And let's start creating the model. Now, most of the data input is done in the general input panel, which is here, currently disabled because the model is currently empty. But there are a few other panels as well available here. So we have design constraints. This is where we can set global information such as a global temperature, pressure, etc. Change the hydro test type, set the MDMT, MAWP, etc. Can all be set from within this panel here. For this example, I'm going to leave everything as the default. And then on the next page, we can set up the load cases. These are the default load cases for the ASME Division 1 standard. If you choose EN13445, you'll get a different set of load cases, but these are the default load cases which satisfy the requirements of the standard, and these are combinations of the various different loadings. Of course, you can change these load cases and you can adjust the default load cases, and if you want to do that and you want to know what the loadings are, you can always hit F1 on your keyboard to open up the help, which is context sensitive, and this will load up the help as appropriate. So here we can see the various different types of loadings that are available. Again, I'm going to accept all of the defaults here for all of the load case options. Some of these loadings are for wind and seismic, which are available on the next 2 pages. Here you can choose the appropriate wind design code or seismic design code and enter in the appropriate information. Same for seismic. And the final page is the header page. This is just heading information which will appear on your reports when you generate the output. For example, I'll just type something in here and we'll see this in the output. So let's start building the vessel. This will be a vertical pressure vessel, and for a vertical pressure vessel we start at the bottom and build upwards. For horizontal, we start at the left and build towards the right. So I'm going to start with the first component, which will be the skirt. So I'm going to do this just by hitting the Insert a Skirt button up here on the ribbon to attach the skirt. Here is my skirt. If I move to orbit mode in the graphics, I can spin the model around, I can zoom in and out using my mouse wheel, as you would expect, similar to a CAD system. But this is not so interesting at the moment. So I'm going to change the length of the skirt first of all. So it's just over 3 meters. I'm going to make it a little bit shorter, 2.5. And then I'm going to add a base ring as well onto the skirt. This can be done by going to the Perform Base Ring Analysis field on the General Input page and check the box to perform the base ring analysis, which allows me to add a base ring. First of all, choose the type of base ring, perhaps one with gussets, and then we can set the various parameters, material data, geometry for the base ring, for the bolts, and for the gusset plates as well over here on the right hand side of the dialog. For this example, I'm going to accept all of the default materials and all of the default geometry data as suggested to me by PV Elite. So I'm just going to click OK. And there is my skirt base ring. Okay, next component will be the first pressure part. This will be the bottom head. So I'm going to go and select to insert an elliptical head, which is inserted like so. It's obscured by the skirt, so if you wish to see that, you can hit this button here to make the shell semi-transparent, and we can actually see the head is placed and it looks okay. However, it's not okay because we see some red text down in the bottom right hand area of the screen. This is calculating that TR, thickness required due to internal, and TREXT, thickness required due to external pressure, is 9.26 and 9.509 millimeters respectively. The MAWP is also 0.4. These are shown in red because, well, my pressure is 0.689 and my thickness is only 6.35. So PV Elite is constantly doing the calculations for me, at least in terms of pressure containment, and I can see immediately this needs adjusting, and I'm going to change the thickness to 10 millimeters. As soon as I make that change, the calculations are rerun, and as we can see now that we are acceptable, all of these numbers have reverted back to the original color. I'm going to reset the view back to the default front view, and I'm also going to turn the transparency off. Now I can continue on and add my next component, safe in the knowledge that my head is acceptable, it's thick enough from the pressure containment standpoint. So I'll next add a cylindrical shell. I'm also going to adjust the length, just round it down to 3 meters. And once again I see some red text down at the bottom of the screen. Again, I can adjust this to, let's say, 13 millimeters. Or alternatively, on the design constraints page, I can choose down here to say select the wall thickness for me automatically for internal or external pressure, or even add stiffening rings or select on axial stress. As soon as I change any of these to yes, for example, external pressure was my issue, as soon as I change that to yes, you see the text is no longer red, and back on the general input page, the finished thickness has automatically been set to 13 millimeters. So again, everything is okay from a pressure standpoint. I'll go on and insert a conical section and adjust the length. Let's change this to, say, 1.5 meters. And let's add a cylindrical section and a second one for the top strake. And let's insert a top head as well. And there we have it. Very quickly, in just a few minutes, we've built the main body of the pressure vessel, and we also know that everything is thick enough from a pressure containment standpoint. Okay, so let's now make a small change and then add some details such as nozzles and a platform to get the pressure vessel ready for analysis. First of all, I'm going to go into select mode and select the cone, and I'm going to change the diameter of the small end of the cone. This top chamber doesn't need to be so large, it can be a little bit smaller, so I'm going to adjust the diameter of this small end, or the far end of the cone. So I'll change that down to 1.25 meters, and as I change that, of course, the model updates, but only the cone updates. The following components don't change automatically. Now that's deliberate. There may be some situations where you don't wish the following components to adjust automatically in diameter. Maybe you want them to be a different size. There are certain situations in PV Elite where that may be the case. However, this is also quite a common situation. So PV Elite, we don't try to be too clever and do things on your behalf, but as a compromise we put this function behind a single button click. So this button here, propagate element diameter. If we hit that button, the model updates and the remaining sections are now the correct diameter. Also, if I just select each of the sections in turn and check down the bottom, our required thickness is 9.77, 9.1, 9.1 and so on. So currently we're at 13 millimeters, which was inherited from the large cylinder in the previous video, but we can actually make this a little smaller. We can get away with this thinner, so less material, less weights, saving us money. So all it takes is a quick check down in the bottom corner, and then I can change this to, let's say, 10 millimeters on the conical section, which is now 10, but the following components are still 13 millimeters. So just like we had with the propagating the element diameter, we can also share other properties as well. So selecting the cone, I'm going to this button here to share information. I can, using the node numbers indicated on the graphics here, 40, 50, 60, 70, I can share any properties that I like, such as the finished thickness, for example. As you can see, you can share other properties as well just by checking the box. Thickness is the only one I'm interested in, so I'm going to check the box and hit OK. And now, selecting the cylindrical sections, I can see everything is now 10 millimeters, but I also see that there's no red text down at the bottom. So everything is okay, but we've saved a little bit of material. So now let's add some details. I'll start by adding a couple of nozzles, one inlet, one outlet nozzle. So let's add the inlet nozzle on the top head. To do this, select what shell you wish to attach the detail onto, which will be the top head, and then select the detail you wish to attach, in this case the nozzle. This brings up the appropriate dialog box for the selected component, and the first thing I'm going to do is change the name of the nozzle. Let's call this N top, and I'm okay with the default material A106 grade B. The flange material down here towards the bottom right, SA105, again I'm happy with that, but what I am going to change is the nozzle diameter. I'm going to change this to a, let's say, a larger nozzle, 350 nominal size. As soon as I make a change to any of the parameters in here, PVE performs the area replacement calculations and the results are shown down at the bottom, and they're shown here in blue. Everything is okay, we've passed. The only other thing I want to do is position the nozzle, but in this instance I want the nozzle in the top center of the head, so I don't need to change any of the dimensional data. I'm also happy with a class 150 flange. The flange rating is checked against the specified pressure, so that's okay. So I just hit OK. And there is my nozzle on the top of the head. Let's add the next nozzle, the outlet nozzle, which I'm going to select here onto the main shell. Select the shell, attach a nozzle, and I'm going to again change the description to N1, but this time I want this one to be exactly the same as the top nozzle. So if you do have a number of identical or similar nozzles, you can very easily use this button here, just like. You then get a list of all the nozzles in the current model. There's only one here, so I'm going to pick the N top. If that gets brought through, you'll see the schedule, the diameter has been brought through, and as soon as I click on and then click off that field to kick in the calculation, I can see the results down the bottom, and these are shown in red, which shows that there is an issue. So here is my area available, 656 square millimeters. I need area required, 1514, so clearly I've failed. You can see the individual areas, area 1, 2, 3, 4, 5, down here as well. So I can see also the effect of making any changes. So perhaps if I thicken this nozzle up, maybe schedule 80, I can see that's made a change down here, but it still failed. What you can also do in PV Elite is this button here, the calculator button, can show the detailed results. So not just the final answer, you can see the detailed results shown here, various different calculations that are done. Here's the results, highlighted in red again where there is an issue. We need an additional 425 square millimeters, but PVE doesn't just tell me there's a problem, it also makes suggestions where possible. So the area without a pad is insufficient. PVE recommends to add a reinforcing pad. So we also get a resolution suggested to us as well. So I'm going to hit OK and add the reinforcing pad, which is done by changing the type of nozzle. This will be an insert nozzle with a reinforcing pad. Changing the nozzle displays the pad section up in the top right of the dialog box. And the default values for the pad, 50 mm wide, 14 mm thick, is sufficient. As you can see, the calculation is now shown in blue, no longer red. The final thing I want to do is move the nozzle. It's currently on the weld, so let's move it, let's say 750 mm along the shell. Okay. And there's my nozzle. Now I can see my nozzle there with the repad, but what I can also see is the longitudinal weld seam. And my nozzle quite clearly intersects that longitudinal weld seam. If we were to run the analysis, PVE would give me a warning about that, but I don't need to run the analysis to see. I can see straight away just looking in the graphics. So very useful having the longitudinal seams displayed. And I can change these by going to the cylindrical shell, going over here to the longitudinal seam efficiency field and hitting the button at the end of the field. I'm going to the longitudinal weld seam data page. And on the cylinder, I can change the angle of seam number 1, and let's just say change that to 90 degrees. Apply the changes and hit OK. And now the seams have adjusted and no longer is the nozzle intersecting a seam. Now let's finish off by adding one more detail. Let's say onto this very top section here, I'm going to add a platform. Select what I want to attach the detail to, and then select the detail I want to attach. My platform. I'll just give the platform a name. Just call it Access 1. And then specify the geometry. The platform, a little bit more geometry required of course than a nozzle, so we have a sketches here to assist us with the input. And so the first thing is, where is the platform located? So this is on a 1.5 meter long shell, so let's move it very close to the top, 1450, and we will go from 0 around to 130 degrees around the platform by the start and end angles. Then for the weights, for the railing, I'll specify a 3 Newton per millimeter generic weight, and for the grating weight, I will hit the button and look up from the database, let's say a 1 1/4 by 1/8 of an inch bars from the grating database. My platform will be 1 meter in width and it will be 1.2 meters high, and the clearance from the vessel, this value here again shown in the sketch, 150 millimeters. And my wind force coefficient I'll put in 1.5. That then computes the effective platform wind area, which is shown in this field here. If you have an irregular shaped platform, or for whatever other reason you've computed the area yourself, you can open that field, make it enabled by checking the box. You can then edit that number. Finally, I'm going to have a ladder on this platform here. The ladder is relative to the platform, so my ladder will be at angle 0 and it will start at 0, which is the platform, and it will stop. I'm going to go down 3 meters. The ladder, I will have again a 3 Newton per millimeter unit weight. It will have a cage, and the total platform and ladder weight is shown here. Once again, if you've computed that yourself, you can check this box to open that field out. And when I hit OK, there is my platform. Again, if I switch to the orbit mode and the graphics, I can spin round, I can take a look at the vessel. But now the vessel, this is complete and it's now ready for analysis. Alright, so we're now ready for the analysis. So to perform the analysis, we can hit on the running man button up on the ribbon shown here. And before we can run the analysis, we must save the file. So I've selected a suitable folder just on my local C drive here, and I'm going to give this example a name. Let's call it storage vessel 001. And then I will hit save, and the analysis will now run. So during the analysis, any critical issues are highlighted as warnings, as we can see here. We have one, the skirt is locally overstressed by the chair or compression ring. We have a second one, the cone to shell junction is not adequate. And then when the analysis is complete, the output is shown to us. As you can see, some of the reports listed in the output are highlighted in red. The vessel design summary is shown in red because we have an issue, the local stress which we know about on the skirt, and the base ring calculations will show us more detail on that, as we can see here. So let's take a look at the base ring first of all. We also have an issue with the conical section, which we know. The conical section also highlighted in red. But on the base ring, I can see that the issue is the combined local plus bending stress in the worst load case, and that is 5,664 megapascals. However, I can also see that the local stress in the skirt due to the gussets is contributing 5,656 megapascals out of that total. It's the weight plus the bending stress is only 8 megapascals, so it's by far, this is the issue, the local stress in the skirt due to those gussets. So I need to do something about that, maybe thicken the gussets up, add some more gussets, or do whatever to make that acceptable. So let's close the output and return to the input. And on the input, I'm going to go to Perform Base Ring Analysis. Selecting that field, that will again display the dialog box showing the base ring information, and in an attempt to more evenly redistribute that local stress that is around the gussets, I'm going to add a continuous top plate. For the moment, I'm going to accept the default geometry for the continuous top plate, so we've got a 45mm thick top plate and so forth. When I click OK, there I can see the top plate, and that local stress that was concentrated around the gussets here should be more evenly redistributed. Hopefully that will be sufficient to resolve our first issue. So let's hit Analyze once more. I do get a warning about the cone to shell junction not being adequate, but when I hit OK, that was the only warning I get, and there is now no longer any issue with the base ring. As you can see on the base ring calculations, no more red text. Everything is acceptable on the base ring. Okay, so I could go and look in detail at the reports, but for this example I'm not going to. There's no red text, so that's sufficient. So let's jump to the conical section report, and once again here I'm just going to scroll down quickly until I see some red text. So I need some additional reinforcement on the large end of the cone. I need another 125.5 square millimeters. And on the moment of inertia calculations at the large end, I see I have 0.173 to the 6 millimeters to the 4 available, but I need 0.23 to the 7 millimeters to the 4. But as we saw with the nozzle earlier, PVE doesn't just tell me that there's an issue, it also gives me advice on how to resolve it. And it's telling me here, if I add a stiffening ring of this size, a bar shape, 9.5 by 88.9 millimeters, that will provide me sufficient area and moment of inertia to resolve my issues here on the large end of the cone. If I scroll down further, I also see I've got the same issue at the small end of the cone. I need more moment of inertia, and I need a slightly smaller shape at the smaller end of the cone, 6.3 by 63.5. So I now have some issues at the large end and the small end of the cone, but what I also know is how to resolve those. So I'm going to once more close down the output and return to the input and add some stiffening rings, one at the large end, one at the small end of the cone, to resolve those issues. So at the large end of the cone, let's select the cylinder where we wish to attach it. We'll attach this right at the top of the cylinder, close to the cone, and add a stiffening ring. Okay, so we could choose a standard bar from the database, or we could enter in the geometry for the bar itself. So I'm going to enter in the geometry, and at the large end we were 9.5 by 88.9. So let's make this 10 mm thick, slightly bigger than our 9.5 required, so that will be sufficient. And for the outside diameter, it will be 2 times 88.9, or 180, near enough, added onto the inside diameter, which is the same as the OD of the vessel, of course. So that would be 2644. That gives us a bar size 10 by 90, which is just about the same as our 9.5 by 88.9. This of course needs to resolve the issue at the top of the cone to shell junction, so I'm going to check the box to specify this is a cone to shell junction ring according to the ASME standards, and that means, well, this must be within 27.5 millimeters of the junction. So I need to adjust the distance, and on the 3 meter shell, if I move this to 980, that is 20 millimeters from the junction. That text now turns blue. This is a cone to shell junction ring. I can hit OK, and if I spin the model round, there we can see our first cone to shell junction ring at the large end of the cone. Let's now do the same at the small end. So selecting the shell connection, placing a stiffening ring, and once again I'm going to manually specify the geometry by typing the dimensions here. So this was a slightly smaller ring. It was 6.3 by 63.5. So I'm going to round that up to 7 millimeters thick, and it needs to be 63.5, which I'm going to round up to 65. So 2 lots of 65 is 130. Added on to the 1270 inside diameter gives me a 1400 mm outside diameter, giving me a bar 7 by 65. Again, slightly larger than the recommendation from PVE Elite. Once again, this is a cone to shell junction ring, so I'll check the box, meaning the maximum distance can be 16.4 millimeters. So let's move this 15 millimeters from the junction. Everything is blue, so this is a cone to shell junction ring according to ASME. Hit OK, and there is my small ring at the top. That should have resolved our second issue, so when I hit the Analyze button, this should be for the final time. And we see no messages, no warnings, everything is acceptable, and now in the output I can see none of my reports are listed in red. I have one orange report, which is the warning that we always get when working in metric, just to inform us that PVE Elite performs all calculations in imperial units internally in order to remain compliant with the ASME standard and the built-in assumptions within those formula. But the finalised results that we see are reflected to show our selected metric units. Okay, now the final stage. Now that our analysis of this pressure vessel is complete and there are no issues, the final thing to do is to generate the report. I'm going to do this, and I've already run the analysis, but I'm going to run it one more time. But before running the analysis, I'm going to hit this button here to generate a 3D PDF file. This will allow me to include a 3D page in my output report, which helps to give everything a little bit more context. So I've hit the button to turn on create 3D PDF files, and I'm now going to hit analyze for one final time. Once again, the analysis runs. And again, no warnings appeared. And in the output, again, we have nothing in red, just the previously mentioned warning regarding the units for compliance with the ASME code. So for generating the report and for sharing with third parties, we can either export to Microsoft Word or export to a PDF file. To export to Microsoft Word, we simply select the report or reports using Shift or Control on your keyboard to select multiple reports and hit the Word document button to export the data to Microsoft Word. Microsoft Word will start in the background and the data will be exported, and you'll see the Word file being built up as it goes ahead. And here's my completed Word file. So I didn't export every single report, I'd only exported a small selection. But you can see it's a fairly small 18-page report. And here we can see all of the detailed calculations, for example on the internal pressure calculations. We see just the same as we see inside PV Elite. In the detailed calculation results we see, here's the calculation, required thickness due to internal pressure. Here's the equation that was used. Here's where that equation comes from, Appendix 1.4c. Here are the numbers that were used in that equation, and here we see the answer. So it's not just a black box, you see the working at every stage of the calculation. I'm going to close the Word file. Our alternative for generating the shareable report is to generate a PDF file. Now the button here will send all of the reports to the PDF file. If you wish to send certain sections and not the entire report, you can do that through the File menu within here. But I'm going to go and export all reports to the PDF file. And the full PDF will be generated, including that 3D page that I mentioned earlier. Here is the completed PDF. And again we see, if I go to, for example, from the table of contents, the internal pressure calculations, we see the same thing as was mentioned in the Word file. We see the detailed calculations, the equation, the numbers used, the equation reference. And what we also see is, if I go to, again, table of contents, I go to the 3D model. Typically you would have to trust the document to access the 3D and enable the 3D view. So if I just trust the document and reopen it, here is my 3D page with an interactive 3D model which you can zoom and pan and spin around to give your report a little more context. And of course this is now a simple PDF document that can be shared with anyone. The report itself is based upon some template files in the PV Elite install folder. So you can change these, you can adjust the logos, the headers, the footers and the title page of the PDF as well. And that's all there is to it.